So Kelsey, you can introduce SangYul.
Yes, okay, great. Yes, thanks again, Daniel. That was super interesting. So now we will hear from SangYul. So SangYul is currently a postdoctoral researcher in the Department of Chemical Engineering at Songkyung University. Please correct me if I pronounce that wrong. He received his PhD in the Department of Chemical Engineering in 2020 from the Sangkyung University under the guidance of Professor Chang Hyung Pang. His research areas include nature-inspired architectures, and through various methods of lithography for multi-scale functional surfaces and applications of bio-inspired adhesive systems, skin attachable devices, and integrated bioelectronics. So with that, I will pass it over to SangYul. Oh, you're muted still.
Okay, can you hear my voice? Okay. Thank you for kind introduction. For the starting the presentation, I'm really appreciating to organizers for giving opportunity to present here. In fact, it is early in the morning in Korea, so my voice may be not good, so please understand. Yes, so my title of research is an Octopi-inspired wet-tolerant adhesive patch for versatile applications. Okay. Let me briefly introduce my research area during the education period and for the future works. My research has been focused on nature-inspired structures for multi-scale functional surfaces in application of bio-inspired adhesive systems, skin attachable devices, and soft robotics with actuating systems. And this is the outline of my presentations. Today, I would like to focus on the discussion of adhesive patches based on bio-inspired 3D suction cups at first. And then I will introduce versatile applications by using conductive microarchitectures inspired by Octopi. For many years, various types of adhesives have been widely used in a variety of fields such as construction, electronics, and medicine. There is hardly any product in our surroundings that does not contain at least one adhesive. Adhesive is any non-metallic substance applied to one or both surfaces of two separate objects that bind them together and resist their separation. Most traditional adhesives react chemically in order to harden as state of the adhesive is changed from liquid to solid. Such chemical moiety-based adhesives are highly strong, permanent, irreversible, and generally toxic. Recently, new types of adhesive have been drawing attention in enabling controllable, reusable, and biocompatible functions. Especially, these features are highly required to apply to human surfaces to avoid various side effects in terms of bioadaptability. As you can see in the forecast report, adhesives show the highest market globally in the medical field. In addition, the annual growth rate of global medical bioadhesive market have displayed a rapid increase. For medical use, biomimetic engineering, which is inspired by the unique structure of nature, has been recently studied all over the world to develop biocompatible and reversible adhesives. To survive in harsh environments, nature organisms have revealed beautiful architectures which induce physical and chemical interactions for attachment. And through recent advancement in nano and microscale patterning processes, many researchers have mimicked microstructures of such animals. In this respect, many researchers are fascinated with particular nature adhesive structures. They reported are of good results to fabricate functional surfaces. And those bio-inspired technologies have been integrated with conventional systems such as biosignal detection sensor or drug delivery systems. From this background, we have to consider some technologies for future healthcare systems with wearable or implantable devices. First one is diagnostic devices with various kinds of sensors to detect many physiological information of the user. And second one is therapeutic system to cure specific disease based on the information previously monitored by the diagnostic device. Here, my research interest is the interfacial layer between devices and human organs, and it also would be important for stable adhesion, biosignal detection, and therapy with drug loading systems. Okay, the PPT is great. Okay, however, previous reported studies have critical issues against human surfaces, including their high body flexibility, irregular surfaces, irritation, and other injury. Most of all, the adhesion properties in wet condition would generally disappear. In summary, to overcome such issues, I have utilized the unique multi-scale architectures in the evolved nature creatures. So first topic is wet-tolerant adhesive with octopus protuberance-inspired microarchitectures. Octopus suction cup have special properties in attachment underwater environment. So we particularly mimic the spear-shaped protuberance in the octopus suckers based on biological new discovery. Such dome-like structure in suckers is known to interplay with adjacent walls and generate additional secondary chambers for strong wet adhesion. These octopus-like microstructures can be fabricated with air trapping molding technique and multiple applications. Herein, we can control the trapped air bubble by using an energy balance between polymer precursor and the surface of master mold. In our measurement, octopus-like patch can get strong adhesion strength as the preload increased in the dry and wet condition, including moist underwater and oily surfaces. For practical applications, our octopus patch can potentially applied in clean transportation of a large area wafer or weight, as you can see the video. Okay, here I would like to explain the underlying mechanism of octopus-inspired like patches. So, okay. First, octopus-inspired the patch are brought into contact with the wet surface. During apply external preload, the spare and the sidewall inside the chambers are in contact. This contact can separate into upper and lower region, leading to a capillary action. And after removing preload, restoring force of the elastic chamber can induce an extremely low pressure in the lower chamber. Simultaneously, capillary bridges in the lower chamber can prevent the leakage of air. Okay, so through fluorescent confocal microscopy, we could observe the behavior of water molecules before and after applying preload. As a result, we demonstrated that the lower chamber is induced to a vacuum-like state by observing the trapped water inside the upper chambers. Our patches also obtained high adhesion strengths on rough skin surfaces. And in addition, our patch would partially help the wound healing processes at the initial stage within 15 days. We found that some growth factors were increased after patch covered on wound, according to mouse experiments and Western blot analysis. Next, we found that the micro wrinkles on the suction cup surfaces would assist to enhance the wet adhesion and water molecule management. So we added soft wrinkles on the previous developed suction cup chambers with protons for high drainability and robust attachment against dry and wet human surfaces. Such adhesive performances can be explained by two mechanisms. First one is drainage of water molecules, and the other is enhanced capillary interactions of the wrinkles. First, during attachment, most of water is pushed out of the patch interface or into the chambers of the microcavities. After release of the preload, water residue remains trapped inside the microscale grooves of the drainable wrinkles due to strong capillary interactions. Therefore, sealing the wrinkles also sustain the suction effect. And second, such micro wrinkles could induce an enhancement of surface area applying in capillary bridges. And we proposed a simple mathematical model to predict the adhesion strengths of the wrinkled patches on the wet surfaces. This bio-inspired adhesive patch may potentially be applied not only against dry and wet human skin, but also various wet organs. On the porcine organs, including hearts and liver, we demonstrated that the robust attachment to our bio-inspired patch could withstand liquid flow. And next, we developed another type of octopus-like adhesive inspired by extruded architectures, which are infundibular and circumferential rim in the octopi. We have had major interest in larger disc-like octopus suckers because of their unusual performances for strong reversible adhesions against dry, wet, and irregularly rough surfaces. The bio-inspired synthetic adhesive is fabricated by simply controlling the meniscus of a liquid precursor during a molding process. It does not involve any hierarchical assemblies or additional surface treatments. The various micro suction cups having different curvature can be fabricated by changing micro hole pattern board because their surface energies are different. We investigated upon experimental and theoretical studies to increase the effective contact area. This adhesion force is mainly attributed to suction stress and capillary interactions between unfoldable microtips and engaged surface. Our adhesive demonstrated stable attachment on moist and hair skin having dual roughness. So we compared with adhesive without octopus-like structures. And lastly, I introduced versatile applications using bio-inspired conductive structure for stretchable electrode. For future applications of skin attachable or implantable devices, we made flexible conductive adhesive patch with octopus-inspired architectures fabricated by various methods such as synthesis of conductive polymer composites, or spray coating of reduced graphene oxide. With high conformity to human skin and water resistant performances, such conductive patches could be applied to stretchable electrodes for monitoring biosignals such as electrocardiogram. In conclusion, our patches could be applied in various industries of clean transportation and the interfacial layer for many kinds of wearable devices. Further than, bio-inspired research can contribute to develop various potential applications from functional surfaces to the integrated smart systems, as you can see. Okay, I'd like to thanks to my advisor, Professor Chang and lab colleagues who helped me. Thank you for your attention, and okay, the time is very tight, so have you any questions?